Welcome to a code report solution video. In this video, we're going to be covering problem 3 from topcoder SRM 733 entitled Hamiltonian Paths in Graph. The question states, consider a directed graph G on n vertices labeled 0 to n-1 with exactly n times n-1 divided by 2 edges. For every pair of distinct vertices I and j, there is either an edge from I to j or an edge from j to I, but not both. Hence, if we ignore the orientation of edges, G is a complete graph. You are given the adjacency matrix of G. More precisely, you are given X with n elements, each containing n characters. For every pair of distinct I and j, Xij is either a plus sign, denoting that G contains an edge from I to j, or a minus sign, denoting that G does not contain this edge. On the diagonal, we have Xii equal to periods, denoting that there are no self-loops in G. A Hamiltonian path in G is a path of length n that contains each vertex of G exactly once. It can be shown that a graph G with the properties described above must always contain at least one Hamiltonian path. Find and return any Hamiltonian path in the given graph G. More precisely, return an array with n elements, the number of vertices in the order in which they lie on your Hamiltonian path. And note that the constraints of this problem, n, the number of vertices, is going to be between 2 and 100. X will contain exactly n elements, and each element of X will contain exactly n characters. So let's take a look at one of the examples that topcoder provided us with. So here's a vector of strings which represents the adjacency matrix of our graph, and so if we set it up like this, we can then create a visual representation of our graph. So you can see here that there is an edge between every pair of distinct vertices, and there is a given orientation. So you can see between 0 and 1, because you see the periods represent there's no self loop. So for vertex 0, we look that there are paths outgoing from 0 to 1 and 0 to 2, which we can see here. And because the minus sign is here, we know that there's going to be, for 3 and 4, edges going towards 0. So this is not explicitly stated in the problem, but this is actually what they call a tournament in graph theory. So you have every edge between each pair of vertices with an orientation. And so the algorithm for this problem is actually pretty simple. Basically, what it's asking us to find is a path amongst these vertices that visits all the vertices. And we are told that this path definitely exists, and there could be multiple of them, so we just have to find it. So the way our algorithm is going to work is we are going to initialize a vector of integers called path, and we're going to initialize this to start with our vertex 0. So this algorithm could work starting with any vertex, but it's easiest to write if we just initialize it with 0. And then what we're going to do is we're going to loop through the remaining vertices. So we'll start with 1, then 2, then 3, then 4, and then just try and find a place in our path that can fit. So we'll start with vertex 1, and so the first place we'll check is putting it at the very beginning of our path. So this is where it would go, and all we need to check is there a path from 1 to 0? So that path doesn't exist, so that's not possible. So then we'll move it 1 position to the right, and then we'll check, is there a path from 0 to 1? Because there's nothing on its right at the moment. So there is a path from 0 to 1, so we'll lock this in as our current path. Then we'll move to vertex 2 and just do the same thing. So we'll check, is there a edge from vertex 2 to vertex 0? There's not, so we'll move it to the right of 0, and we'll check, is there a edge from 0 to 2 and 2 to 1? And there is, so we will insert our 2 into this spot in our path. And now our Hamiltonian path at the moment is 0 to 2 and 2 to 1. And then we just continue to do this. So for vertex 3, we'll check, can it go at the beginning? So we check if there's an edge going from 3 to 0. There is, so we'll lock that in. And last but not least, we'll look at vertex 4. So first we'll check, can it go to the beginning? At the beginning of our path, so is there an edge from 4 to 3? There's not. We then check, is there a path from 3 to 4 and 4 to 0? There is, so we'll insert our vertex 4 in between 3 and 0, and this will be our final Hamiltonian path. So it's actually a very, very simple algorithm. I guess you just need to be aware of the fact that this is a way that you can implement this. And because we know that the number of vertexes or vertices is going to be between 2 and 100, And although the runtime, the complexity of this algorithm is going to be cubic, 100 is small enough that it will work. So let's take a look at our code. So here it is pretty simple. We just have our function findPath, which takes a vector of strings, which is our adjacency matrix. At the top, we're just initializing our vector of integers path to be equal to 0. So note, like I said, you could start with any vertex that you wanted. You would just have to modify the first loop. So note that we're leaving 0 out of our first loop. So if we modified this just so that it would skip whatever we initialized our path to which vertex it started with, this algorithm would continue to work for any vertex that we started on. So then once we have this, what we're going to do is we're going to loop through the remaining vertexes or vertices, and for each vertex we are going to loop through all the different positions in path. So it will grow longer and longer, the checks, as this algorithm progresses. And then we just have two checks. So we're checking to see is there a path from our current vertex to the vertex that'll be on the right, and is there a path from our current vertex and the one on the left. So going from the node on the left to the vertex, and the vertex to the one on the right. So when we are at the beginning and the end of the list, we have to check to make sure that our index j is less than the length of our path, and that when we're checking on the left that j is greater than 0. And we're also checking that these edges exist in the direction we want them to. So if they're not equal to a plus sign, then we're just going to skip over and go to our next position in our path. And if we can satisfy or get past both of these conditional conditions, we're going to insert it into our path just using our .begin plus j, and then break out of our loop. And we're going to do this for each vertex, and at the end we will have our path. So as I mentioned before, the time complexity of this algorithm is going to be cubic because our first loop is linear, our second loop is linear, and our insertion into our vector is also linear.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.